All right, and now we are going to continue on to 2D defects. So grain boundaries, external surfaces, phase boundaries, twins, stacking faults, etc. So most important, probably, obvious defect is just a surface. So bonds at the surface are not satisfied, increases surface energy, increases surface tension. For our discussions on mechanical behaviors of materials, grain boundaries are going to be of critical importance. So grain boundaries are very, 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 actually super important for many reasons. But they also play a key impact as you cold work and as you increase the density of dislocations, you decrease the essentially the grain size. So grain boundaries basically separate where I have rows of atoms, perfect crystals going this way, and there's an angle and there's a shift. As you can kind of see here, as I'm kind of highlighting, there's a shift, an angle that basically there's this misorientation of grains. So the larger your grain size, the more orientation you have. Lower your grain size, again, that is going to affect essentially your mechanical properties as well. So those are very, very important grain boundaries. Twin boundary, basically you have some special mirror symmetry. So you'll see this often. So in FCC and BC, actually annealing twins are required in FCC, but in basically in HCP crystals, when you have stacking, so for FCC, when you kind of create those materials, you have this ABC stacking. For HCP, you have AB, AB, AB. But when you are doing it, or when you're actually examining those materials, when you have a twin boundary, you're just basically having this mirror symmetry between them. And it can happen quite often in shear stresses and then annealing. Stacking fault is you have basically either an additional layer or an extra layer. So if you have a missing layer, that's an extrinsic stacking fault. So it'd be like A, B, C, and then you're missing an A. An extrinsic is if you're adding an additional layer in there. So A, B, C, and then C, A, B, C. That could be an extrinsic stacking fault. Stacking faults are actually very important. They're related to stacking fault energy. Those will also highly affect, again, they're very important in the automotive industry and a lot of metallurgy fields. Excellent. You can also have antiphase boundaries or interphase boundaries. So basically, very similar to when you're kind of trying to integrate different structures. So if I have, a matrix of FCC and then I have a little, part of BCC right here, a little precipitate, you're going to have those antiphase or interphase boundaries. So those are the majority of the 2D defects that you're going to kind of see and encounter in this class. And then next time we'll get into bulk or volume 3D defects.